Hello. This lecture will cover pages 33 through 40 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Basic Filters, Chapter 6F. We're going to be discussing filters in a lot of detail when we work with Bode plots coming up in the 14th and 15th week of the course. But for now, this chapter introduces them and I want to talk about them. We're going to start on page 33. As a quick summary here, we're going to look at passive low-pass filter. Then we're going to look at an active low-pass filter. Then we're going to talk about a passive high-pass filter. And then finally, we're going to discuss an active high-pass filter. So starting back on page 33, filters have lots of applications. But for now, I just want you to understand the basic concept behind them. I want you to notice, first of all, when we talk about a passive filter, we're talking about a filter that uses all passive elements. There's no active elements, like an operational amplifier, as part of the filter. This particular passive filter is a low-pass filter. And I'll explain that characteristic in a minute, but I want you to see that the resistor is placed up here and the capacitor is placed down here. We have an input voltage coming in on this side, with this being a ground reference. And we have an output voltage over here, and we want to find out what's the transfer of this voltage V in to V out. That's all we want to find out. We want to find the transfer of the voltage in to the voltage out. We refer to that as a transfer function. So if you take a look, the resistor we know has resistance. Ideally, the capacitor does not have resistance. The capacitor has impedance, and the impedance of a pure capacitor is referred to as capacitive reactance. Now, we may have discussed capacitive reactance. I don't know if it's in the next chapter or we've discussed it already, but this value of capacitive reactance can be treated just like the opposition to current flow that it is, just like up here. So if we want to find the output voltage with respect to the input voltage, that's the voltage divider rule. Take a look here. V out is equal to V in times the value of this impedance, which is capacitive reactance, divided by the sum of the capacitive reactance and the resistance plus the capacitive reactance. So forming the ratio, we'll get the voltage gain of this circuit. The voltage gain of this circuit, A sub V, is simply equal to V out over V in, which is equal to X sub C over the quantity R plus X sub C. I hope you can see what that's telling you. That's the transfer function. That's the transfer function of that circuit. It's the voltage gain of that circuit. Now, very important concept here. What we basically said was that circuit can be reduced down to a block diagram where we have a voltage in over here. We have a voltage out over here, this circuit, and its transfer function is X sub C divided by R plus X sub C. That's the transfer function. So all you have to do in circuits in the future is you just have to look at the voltage divider rule. You look at the voltage divider rule and you just use the reactances and resistances. You just use this part of it. So can you look at that circuit and just think in terms of X sub C? That resistance there, that element there, divided by this element plus that element. Boom, you go right to the transfer function. Once you see that, it makes your life a lot easier. It will in the future as well. We'll revisit that in a minute. So here's the transfer function. And we're going to evaluate that transfer function for 0 is less than or equal to the frequency in, which is less than or equal to infinity. So this frequency here can go from DC, which is 0 hertz, up to some infinity hertz, some real high frequency. Notice that this Vn is time sensitive right here, and it has a frequency component to it. And we're going to vary that frequency component from DC the whole way up to infinity, and we're going to see what happens up here. We already know from a previous discussion that at the frequencies at DC, when the frequency in here is equal to DC, that capacitor looks like an open circuit. So here's the transfer function up here. The transfer function says X sub C over R plus X sub C. Well, at DC, the capacitor looks like an open circuit. That's infinity ohms. So you replace X sub C with infinity plus R plus infinity, and that's equal to 1. So at the very, very low frequencies, the transfer function is 1. Don't forget what the transfer function is. It's the ratio of output over input. So go back up here. You have 5 volts in, and this looks like an open circuit. There's no current flow here. That's an open circuit. 5 volts in, no current flow, you get 5 volts out. 10 volts in, 10 volts out. 100 volts in, 100 volts out. Form that ratio. It's always 1. So if we do a plot down here of the voltage gain versus the frequency, here's the voltage gain, here's the frequency. Notice that at a particular frequency, I'm going to call just F prime. I'll show you how to calculate that coming up in a couple lectures, or well, in about 3 weeks. But at a particular frequency, we'll call that frequency at this point right here. Below that frequency, it basically looks like a direct transfer of voltage. It's 1. This is the ratio here, V in over V out. It's 1. The whole way down to DC. No, DC isn't shown here. These frequencies get smaller and smaller and smaller and smaller, but you just approach 0 frequency. There's no label of 0 frequency on this axis at all. And as you go in this direction, the frequency gets higher. Well, let's take a look at frequencies approaching infinity. Well, we know at very, very high frequencies, the capacitor looks like a short circuit. We discussed that in the past too. That's when you first close the switch, remember? It looks like a short. When you first close that switch, that's a real high, that's a step function. That's a very, very high frequency component. So here's a transfer function. X of C is 0 over R plus 0. You get 0. You don't get anything out. Why? Because all the voltage here, this gets shorted to ground. This is a short, and you're down here. If you take a look at the characteristic of that, you basically have a 1 transfer function up to a certain point, and then at some frequency, no, it doesn't make an abrupt transition here. A good rule of thumb is, and you'll find this out later, is you go 1/10 of a frequency down, and the effect of that filter has already reached the point that it's not going to make any more additional change to that circuit. So at 1/10 the frequency down, you already got the full effect of the filter, and at 10 times the frequency up, the effect of that filter has diminished, or has ran its extent. Notice this: at the low frequencies, you pass the signal. At the higher frequencies, you kill the signal. That's what a low pass filter does. It passes the low frequencies and it kills the higher frequencies. Why? Because that shorts out. Let's take a look at an active filter. Here's an active low pass filter. Notice it's active because we're using an active element. We're going to sketch the transfer function here, the gain, V out over V in, as frequency goes from DC to infinity. We'll just take a look at that circuit right there. And remember what the gain of that circuit is. At frequencies equal to DC, or approaching that 2 microfarad capacitor looks like an open circuit. At DC, that looks like an open circuit. Therefore, the absolute value of the transfer function, and we only care about the absolute value here, is equal. If that's just an open circuit, you get 10K over 1K, you get 10. The absolute value of it's 10. So plotting this, just the absolute value down here, you get 10 at frequencies below. At 1/10 the frequency. And what about our frequencies approaching infinity? Well, that looks like a short. So if that capacitor looks like a short, it shorts out to 10K, and in the numerator here you get 0 over 1K. The absolute value of that is 0. It kills the frequency. Now, there isn't an abrupt transition like this. You already know that. It's a gradual thing. You'll see on our Bode plots later on. But if you look at that, you can see that is a low-pass filter. It passes the low signals with a gain of 10. It passes the low-frequency signals with a gain of 10. And anything above, whatever this break frequency turns out to be, which we'll calculate later, it kills the signal out. And you should be able to see that here through what I just explained here. Or just simply look at this, and at the high frequencies, that looks like a short. And there's absolutely no gain to that circuit. Let's take a look at high-pass filter. I want you to use the same techniques that I used in a passive low-pass filter. Notice we're putting the capacitor up here, we're putting the resistor down here. You should be able to look at that circuit and come up with the transfer function. The transfer function is the voltage gain, V out over V in. It's R over X sub C plus R. There it is. Real easy to go from here to the transfer function here. You shouldn't have to go through this step up here. We're going to evaluate this for zeros less than or equal to the frequency, which is less than or equal to infinity. This is a voltage coming in here at a variable frequency. And we're going to see what it does. Does it pass the low pass? Does it pass the high pass signals? What does it do? Well, if you come down here and take a look, at DC, at frequency approaching DC or equal to DC, that capacitor looks like a open circuit. So put that into the gain formula here and you get 0 gain. That's open. Nothing can make it to here. You're down here. 0 gain. That's 0 gain right there. This is gain in this direction. Then at some break frequency, a decade below or 1/10 below, that filter is no longer, it has already completed its course. At a decade above, it finalizes the transition. And that's done right here. At frequency equal infinity, I want you to notice that the gain is R over X sub C plus R. X sub C at very high frequencies looks like a short. So you get 1. So you're back up to 1. Notice that filter. Now there's this transition here, remember. It doesn't happen abruptly because of the reasons I've explained here. But I want you to notice that just by looking at this waveform right here, I think you can see that is a high-pass filter. It's passing the high-pass frequencies, and the low frequencies are not allowed to pass. That has a lot of application. It's a passive high-pass filter because it doesn't use any active devices. Then finally, let's look at an active high-pass filter. Notice what we're going to do in this case is, by looking at this circuit, you can't see this right off the bat probably. But let's take a look at that circuit and let's determine whether it's a high, you know it's an active filter because it has an active device in it. But is it a passive? Is it an active high pass filter or is it an active low pass filter? Well, let's check it out. We're going to sketch the absolute value of the voltage gain, which is V out over V in, for all range of frequencies. At DC, at F sub I, at the frequency here at DC, you can take a look at this and that capacitor is going to look like, what's it going to look like at DC? It's an open circuit. So you basically have, with this right here being an open circuit, this is all open here at DC. That 1K doesn't even come into play because it's in series with infinity. Infinity plus 1K is just infinity. So forget about that. So the gain is 50K over 10K, which is 5. So the gain down here at the low frequencies at DC, let's say 0.01 hertz. Remember, you can't get to DC here. It just approaches DC. So at these low frequencies, and we're not even going to specify this point right here. It's some break frequency, F sub B, which we'll calculate later. Don't worry about that. It's just a time constant between the values of resistance and or the values of resistance and capacitance. Pretty easy calculation there, but that's not the concept I'm trying to get to you here. I'm just trying you to see that at the low frequencies it has a gain of 5. And what about at the high frequencies? At the high frequencies, this here looks like a short. So basically you have 50K over the parallel combination here. Well, 1K in parallel with 10K, let's just round it off. It's 1K. So you have 50K divided by 1K. Well, the gain of that circuit, being an inverting amplifier, would be a negative 50, but we're taking the absolute value to plot here. So that's how you get 50. So at the high frequencies, you have a gain of frequency. You have a gain of 50. So taking a look at this as a summary here, at the low frequencies, you have a gain of 5. At the high frequencies, you have a gain of 50. There's a transition in between here somewhere. Don't worry about it. But you can look at that in general, and you should be able to say that it is a high-pass filter. It's passing the signal of it's passing the high-frequency signals at a higher gain than it's passing the low-frequency signals. That makes it a high-pass filter. May give you something like that on a quiz or an exam, just to make sure you can just rationalize through this. All you have to do is know what a capacitor does at DC, and what a capacitor looks like at DC, an open circuit, and what a capacitor looks like at high frequency, which is a short circuit, and just analyze these from the gain standpoints. That's all. And that concludes this lecture and this chapter.